righty. So this is going to be Physics 102, Chapter 21, Magnetic Forces and Magnetic Fields. So if you look at the needle of a compass, the needle of a compass is a pyramid magnet that has a north magnetic pole on one end and a south magnetic pole on another end. Now, the behaved magnetic poles are actually similar to like and unlike charges. Same north and north, south and south, they repel. Same ones repel, opposites attract. So surrounding a magnet, there's something called a magnetic field. The direction of magnetic field at any point in space is the direction indicated by the north pole of a small compass needle placed at that point. It goes in from the north to the south. Now, magnetic field lines are patterns of iron filings in vicinity of our magnet, and magnetic field lines in the gap of horseshoe magnet. Let me just, actually, I have a video of this. Let's actually go look at these two videos first. That's where you get opposites attract. All right, let's go look at the second video. Notice that the fields between the ones that are the same, there is almost none existent. Okay, let's look at one more video. All right, so basically, let me just put this in. So on a charge, let me go ahead and write this down. is placed on an electric field, it experiences a force. This force is going to equal to that charge multiplied by the electric field. Now, that's where we're going to introduce something called beta. And that would be the magnetic field. And let's say F, that's a force on the charge. Now, your electric field is actually gonna equal to something called the velocity of the charge cross beta, which is your magnetic field. Now, let me actually explain this. Let me go this. When you have a cross product, it's called a cross product. Now, when you have a cross product, A cross B, that's going to equal to the magnitude of A multiplied by the magnitude of B multiplied by the sine, the angle between them. So, when you have V cross B, this is going to equal to VB sine theta. And again, let me actually put this. This is going to be the velocity of the charge. And Q, that's your charge. So really, if you actually substitute this, your force is going to equal to the charge multiplied by your velocity of the charge multiplied by the magnetic field set done by that charge multiplied by the sine, the angle between them. Now, if you solve this for the charge, Q not charge, the magnetic field beta. Let me actually get a blue. Let me get this. So if you actually solve for beta, what you're gonna have? You're gonna have F over QV sine theta. Now, your theta is gonna go to 90 degrees, so that's gonna go to 1. So what you're gonna have your force divided by your Q multiplied by your V. So your magnetic field is going to equal to the force multiplied by the charge divided by the charge multiplied by the velocity of that charge. Now, if you actually work out the units for this, what you're going to have? You're going to have newtons for your force multiplied by coulombs for your charge multiplied by your meter per second for your velocity. So let me actually go ahead and label these real fast. Newton, seconds, meter, and coulomb. Now, and let me just close this. Now, your Newton seconds per coulomb meter, that's what we call the Tesla. We give a big letter T, which is your Tesla. So your magnetic field again is your force divided by QV sine the angle between them. When the angle, when the angle is 90 degrees. Now, and so this is going to be called the Tesla, which is going to be the unit of the magnetic field beta. Now, supposedly you have a charge. Let's say this is the orbit and this is your charge. Let's say you get a different color for the charge. Supposedly I have a charge. Let's say this is the positive Q going in. That's going to have a velocity v, again, like we saw from chapter 2. And this is going to have an inward force towards the center, where this is your radius r. So you're going to have a v, a velocity going in with the q. That's where you bring us to your centripetal force, which is your mv squared over r. Now we said that our force is going to equal to q multiplied by v multiplied by b from this one. If we had the magnetic field equals qvb, that means your force is going to equal your magnetic field multiplied by the charge multiplied by velocity. So qvb is going to equal to mv squared over r. Now, one of the velocities cancel out. So what you have is your charge multiplied by your magnetic field is going to equal to mv over r. That means your radius is going to equal to mv over q multiplied by your beta. Now, that's what brings us to the so actually, let me go before I go. So let me actually go. So we said that the force was q multiplied by v cross b. Now, again, your v is your velocity, which is your distance over your time, which is your length over your time. And this distance, again, this is the distance the electron travels. So your force is going to be q multiplied by, if you substitute that in it, where L over T, what you're going to have? You're going to have 1 over T multiplied by L cross B. And we said that there's going to be Q over T, L cross B. Now, remember from the last chapter, we defined the charge over time as your current. So that means your force really is going to equal to your current multiplied by your L cross B, which is going to equal to your I multiplied by your absolute value of the length multiplied by the absolute value of the magnetic field multiplied by the sine of the angle between them. Again, let me actually write this down. So this is going to be your change of charge divided by change of time. And this one will be actually your length, which is going to be your V delta T. Now, if you have a wire, let's say you have a wire that has 5 amps going through it, equals 5 amp. And you got a magnetic field around it. Now, this magnetic field is going to follow something called the right-hand rule. So your right-hand rule is, let me go ahead and try to draw it. So let's say this is your hand. 1, 2, 3, 4, 5. I'm going to do my best to draw a hand. So your thumb that's where your current is going. Your fingers, that's where your magnetic field is going. Coming out of your hand, that's your force is going. So if you actually apply this one over there, what you're gonna have? You're gonna have the force going on top where you got the magnetic field, because X those are magnetic fields. Magnetic fields going inwards towards you and then going inside. So what is the net force? That's your right hand rule. So what is your net force of this magnetic field? Let's say on a 2 meter section of the wire. So let's say let's say we have back our wire, you got a current going and I, which we defined as 5 amps. And we're looking at a 2 meter section of the wire, which is your length that we're looking at. So the magnetic force, the force is gonna equal to, the net force is gonna equal to QVB sine the angle between them. Now the angle between them, don't have it, so it's gonna be 90. So it'd be your 5 amps actually, hold up, before I do add that, let me just go ahead and write this down real fast. It's gonna be equal to QVB sine theta, which is ILB sine theta. So we're gonna be using the ILB sine theta, which is gonna equal to your 5 multiplied by our length 2 multiplied by your magnetic field, which is gonna be 1 Tesla. We have not defined it, have we? Let me go ahead and write this down. Where your magnetic field equals 1. Forget to write this down. So your force is going to be 2 times 1 times 5 multiplied by sine your 90 degrees, which is going to equal to 10 newtons. Now that's what brings us to the net torque. Now your net torque your tau is going to equal to NIA B sine theta. Now N is going to be your number of turns. In the wire. I, that's your current. A, that's your area. Now, when did this happen? Let's say you have a shaft going in. And in this shaft, you got a south magnet and you get your north. So what's happening to the shaft? The shaft is actually going in and turning from north to, actually, sorry, it's gonna be from north to south, it's gonna be this way. It's gonna go ahead and be turning. So this is the shaft and you got a current going in, go the way I, and going in this way, I, right? So your torque that's going in is the number of loops that this is happening. Multiplied by the current, multiplied by the area of it. So, now for our long straight of wire, your magnetic field is going to equal to mu naught I over 2 pi r. Now we have defined mu naught from previous classes as your permittivity of free space, which is going to equal to 4 pi times 10 to the negative 7 Tesla meters per amp. So with the force in the long straight wire being Q V cross B, this is going to equal to QVB sine theta, which is going to equal to QV, and then just substitute your magnetic field in there. So this will be QVB sine theta. This will be QV mu naught I divided by 2 pi r sine theta. Now for a circular loop, this is what you get a long wire. So this is like if you have a wire in it. Now let's say you get a circular loop going in. So for a circular loop, your magnetic field is going to equal to mu naught I over 2 multiplied by r, the radius. So and that brings us back to this. So the charge, your force on the charge is going to equal to the charge multiplied by the electric field. Now, we just showed the magnetic field, which is going to be, well, actually, is your force is going to equal to the charge multiplied by the magnetic field multiplied by V sine theta from that cross product. So where your magnetic field is going to equal to your Newton seconds per Coulomb meter, which is going to be your Tesla. So let's go ahead and do a question over here real fast. So you got a proton accelerator has a speed of 5 times 10 to the 6th power meters per second. The proton encounters a magnetic field whose magnitude is 0.4 teslas and whose direction makes an angle of 30 degrees with respect to the proton's velocity. Find the magnitude and direction of the forced proton, the acceleration of the proton, and what would the force and the acceleration of the particle were an electron. So we got a speed of 5 times 10 to the 6th power with a 0.4 Tesla. So let me go ahead. So this is going to be example 1. So you got your speed, which is 5 times 10 to the 6th power meters per second. And your magnetic field is 0.4 Teslas. And your angle is 30 degrees. Now, for A, you want to find the magnetic direction of the force on the proton. So your force, that's what we need to find out, which is going to equal to be QVB sine theta. So it's going to equal to the charge of the electron, 1.6 times 10 negative 19, multiplied by that velocity, 5 times 10 to the 6th power, multiplied by your magnetic field, which is your 0.4 Teslas, sine the angle between them, which is going to be 30 degrees. And plug it in. At 1.6 times 10 to the negative 13 newtons. Part B. Acceleration, we need the acceleration of the proton. So the force, which is going to, of course, equals your mass times acceleration. That means your acceleration is going to equal your force divided by mass. Which mass? The mass of the proton. Now, the force again was 1.6 times 10 negative 13. That's what we found out. Divided by the mass of the proton, which is still would be 1.6 times 10 negative 27 kilograms. So you should get 9.6 times 10 to the 13th meters per second. For part C, now we're needing to find the force for the accelerator of the particle in an electron. So same thing, where acceleration this time, your acceleration is going to be force divided by the mass, but this time you're talking about the mass of the electron, which is going to be 1.6 times 10 to the negative 13, divided by the mass of the electron, which is going to be 9.11 times 10 to the negative 31, and you should get 1.8 times 10 to the 17th meters per second squared. Second squared too. And that's exactly what we just did. Now, we also look at the magnetic force also remains perpendicular to the velocity and is directed towards the center of the path from the centripetal force, which is mv squared over r. We said that the qvb was going to equal to mv squared over r. When the velocity cancels out, so your radius equals mv over qb. Now, and this is the right-hand rule that we tried to draw. So basically, if you actually put your hand up, your thumb, that's where your current is going. Your fingers, that's where your magnetic field is going. And on top, coming out from your palm, from your middle of your hand, that's going to be your force. Now, your force is QVB sine theta, which is Q over delta T. We said that was your I, multiplied by your V delta T, which is your L. B sine theta, so your F equals ILB sine theta. There's another question over here. Go ahead and pause this and work on this question real fast. We also talked about the torque, where the torque equals NIA B sine theta. So let me go ahead and do an example on this. We got example number 6. You got a wire that has an area of 2 times 10 negative 4 meters squared, consists of 100 loops at a current of 0.45 amps. Let me go ahead and do this one. This is your example 6. So your area is 2 times 10 negative 4 meters squared. Your loop is 100 loops of wire. And your current is 0.045 amps. And your magnetic field is 0.15 Tesla, and the magnetic moment. Okay, so your magnetic field is 0.15 Teslas. And we're looking for the magnetic moment. The magnetic moment is NIA. That's called the magnetic moment, which we're looking for. So your NIA is going to equal to your 100 multiplied by your current, which is 2.045, multiplied by 2 times 10 negative 4. So that'd be 9 times 10 negative 4 amp meter squared. Now, we found that we need to find the torque. So in order to find the torque, it's going to be NIA multiplied by the magnetic field, multiplied by sine the angle between them. Now we found that deals 3, that's gonna be 9 times 10 negative 4, multiplied by 0.15, multiplied by sine the angle between them, which we didn't have one, so we're just gonna go sine 90, which is gonna equal to 1. So it'd be 1.4 times 10 negative 4 Newton meters. Yep, that's what we got. So now for a long string wire, the magnetic field is gonna be mu naught I over 2 pi r, and again, mu naught is the permittivity of free spaces, is 4 pi times 10 negative 7 Teslas. And when it is in a loop of circle, a loop of wire, your magnetic field would be mu naught I over 2 pi over 2r, where r the radius. So go ahead and pause this video. There's a good example over here that actually substitutes these two, which you're gonna have to do the difference between the one in the circle versus the one in the wire, the loop versus the wire, and go ahead and plug the equations and see if you can get the answer. And this is gonna be concluding chapter 21 for physics 102. Let me go ahead and stop share. If you have any questions, email me at abunaem@ua.edu, or you can give me a call at 256-348-1480. Thank you.